Good morning. We are almost through with water. I'll just take about 5 minutes and wrap it up, one or two points, and then we will move on to fertilizers. We, of course, discussed the methods of estimating BOD and COD, and we also discussed methods by which COD and BOD can be removed, or COD particularly can be reduced. Okay, I mean all the chemical treatments. But the thing is that there's nothing as nice as being able to treat the effluent biologically, if that's possible. And we have also seen how even things which are biologically recalcitrant, even those chemicals can be converted into a form after which the biological degradation can kick in. So biological treatment is very important, and that's what all the companies have their effluent treatment plant for. They really work on biological treatment. Few of the things that we should remember is that in case your biological treatment is not effective, then you'll have to look at other methods. Like, for example, advanced oxidation techniques are known, like you can use Fenton's reagent or hydrogen peroxide or ozone. These kinds of techniques have been developed. Usually, they're not practiced that often because there's a very high cost in doing that. Another is not really looked at that much, but it would make a lot of sense that if you have got organics in your water, why not just pull it out with an organic solvent, and then you can greatly reduce the volume. Okay, and then after that, maybe that small volume can be incinerated. So that might be another way to do it. There are also things like thermal oxidation, catalytic oxidation. So these kinds of processes are also known to get rid of these organic. I mean, so that's one of the important things to make a note of, that if you cannot do the treatment biologically, then you may have to do all this. Now, let us look at actually biologically how exactly biochemically how these things are done. The process is really an aeration process. Okay, so you are actually doing an aerobic degradation. Okay, and so you take your effluent, and aerate it, and then of course you have to also have a consortium of bacteria which will do the degradation. Finally, you allow it to settle down. Then you get a sludge, and this sludge will have actually most of the bacteria that you have used, in the process, and this will be a clarified water, which is a treated water. Either it can be discharged to drain, or if you feel that you might be able to recover some water from this treated water, then of course you can do that, also recover some water. But it depends on what is the quality of the treated water. And then the sludge that you get, a part of it is recycled, because you need to again have the bacteria doing the job. So part of it is recycled, and the rest of it is a sludge which will have quite a high proportion of water also. Then one has to squeeze out as much of the water as possible, and so that you are left with a dry sludge, which can either be burned, or sometimes people recover energy from the sludge. You can do that also. And there are methods known for efficient dewatering of the sludge. That's known. Like, for example, there's a chemical called volute. I was seeing these people do this, and it's a efficient way of doing the dewatering of sludge. You can also do it by pressure filtration, but the problem is that sometimes the pressure can cause the microbes to die. Of course, it may not matter if you are recycling this, and then the rest of it, if you're doing a pressure filtration, then that should be okay. There should be no problem in doing it. But always remember that all of these things naturally cost money. There's additional processes involved. But this whole business of not only the removal of the organics, but finally also being able to settle the all the dirt and get a clear water is sometimes a very imposing task. So a lot of research has also been going into this area. Now, there is another aspect that you need to look at. You see, it's an aeration process. So you're taking your water and you're sparging with air, and then you're doing aerobic processes of degradation. Now, do you see any problem with an aeration process of this kind?
Other impurities may be added when it is exposed to air or air is added.
I mean, you are saying things which might come from the air, right?
Yes,
That's what you're
yes, sir.
trying to say?
Yes, sir.
That's a good point. If, for example, if it interferes with the biochemical degradation, so you're saying airborne impurities, okay?
Yes.
I think that's a good point. It could affect, okay. Any other thing that comes to your mind?
So the air that is introduced, does it
Yeah.
have to be introduced at a certain pressure?
Yes, it has to be because you have to sparge it. No? So there has to be a positive pressure which you are applying, but probably no more than half a kg or so. It
Okay.
won't be a very high pressure.
Okay, sir.
Okay. Any problem? You see, your raw water can not only have non-volatile organics, but they could also be volatiles, right? Volatile organics may be there, and then when you are sparging like that, obviously the low boiling things can end up in the atmosphere, right? In fact, I remember I had taken the job batch, but maybe about 3 years back, to a company in Bangalore to their plant, and we spent the larger amount of time on the effluent treatment plant. And I was feeling a lot of smell over there, and I asked those people that could there be things because why I'm smelling things, which means that something much must be going into the atmosphere. In fact, one of them was very honest, and he said, "Yeah, yeah, most of it goes into the air." Sometimes these people insist that you let us sparge with a higher pressure. I think what they're trying to do is let it all escape into the atmosphere, and nobody is monitoring that. So I think as engineers, you should not only look at the positive aspects of what people say. For example, I'm always skeptical about some of these things. That's what made me ask this question. I think that this has been grossly overlooked. Escape of volatiles during sparging is being overlooked. This is actually important, and just make a note of it. So you should be critical about whatever you learn. Everybody sweeps these uncomfortable questions under the rug. See people asking these questions, and I'm surprised sometimes. Why is it that nobody is asking the question at least? And that's why I put over here, what about volatiles in effluent? Can they not get released into the atmosphere? So remember that there are certain pitfalls in this process, but by and large, this is a very standard method of treatment, and especially if there are non-volatile constituents, then of course there should be no problem. But in an open system, if there are volatiles, then I would be a bit wary of those, and I would first strip off those volatiles before putting it for treatment. Maybe do a solvent extraction, get rid of those kinds of organics, and then do the rest of it. Now, another is I see this as a wasted opportunity. Can you tell me why? Why do I see it as a wasted opportunity? This process. I mean, not in all cases, but in some cases, it could be a wasted opportunity.
So please could you explain the question a bit? Like,
No, I'm just saying that you are putting raw water, which has got some organics, and then you are degrading it by this aeration tank. Then, of course, you are getting treated water, and all that is fine. But I'm saying that this kind of method of treatment, you could also view it as a wasted opportunity. What is that opportunity I'm talking about?
So we could reuse these organics for some other process.
You're talking about recycling some of these organics in your process and things like that, right? Yeah, that you should try and do upstream itself before allowing it to come to the effluent treatment plant. But that's a good point. In fact, whatever I am thinking of is not very different from what you're saying, but maybe slightly different context.
so use
See,
this water for as a cooling agent or something.
no, that you will do after you treat the water. This treated water you can use for some of those applications. Yeah, so there will be applications of the treated water. So that would be good. I mean, good thinking. The question I'm asking is there any need to, and I think one of you has said so nicely that you can think of recycling some of the organics. In fact, what people are also looking at is that if I've got a fair amount of organics, why do you want to convert it into carbon dioxide? If you, for example, do an anaerobic process, then you might be able to convert those into methane, biogas. Like, for example, distilleries do. I mean, all the distilleries, after they recover ethanol, they get something called spent wash, which is quite high in organics. What they do is that they do an anaerobic digestion and recover as much biogas as possible. And then, of course, the rest of it is further treated. But they recover energy. So
So, but
whenever
can't
you've
this
got something with a calorific value, just think of recovering some energy from it. I'm not saying that it will be successful everywhere. And if the amount of organics is too low, then it may not be practical, to do it. But if your organic load is fairly high, then, instead of doing this sparging and aerobic decomposition, you may want to do an anaerobic process.
so but can't we utilize the CO2 in a process such as Solvay process?
Oh, yeah, you can use. See, one is, of course, there has to be a proximity. Whatever you want to use it for, it has to be in the vicinity. Secondly, I think that, yes, CO2 definitely commands value, but not as much as, let's say, biogas. Okay, because this CO2 also, you'll have to, it's coming out along with air and things. So you'll have to compress it, it's coming out with a low concentration. So you cannot just use the CO2 like that. You'll probably have to do some kind of a purification. And in fact, if some of these organics coming out, whatever I was telling you, if the CO2 comes out along with some of these organics, then again, it may require a costly process of purification. Have I answered your question?
Yes, sir.
Okay. Okay. Yeah. No. So, and I also mentioned to you that this clarifier settler is again a very important part, and many times this is the rate limiting step. Otherwise, you may have to have tremendously large hold up tanks where you put this, and which may not be practical. So, in fact, now people are trying to rush this, hurry this process, and so instead of the natural settling process, as I told you, one is that you can use these chemicals like volute, which are flocculants. And another thing which has become quite popular is what is known as the membrane bioreactor. You have a membrane module where actually this degradation is taking place, this biochemical degradation. Maybe the bacteria, etc., are attached to the membrane. And then after it has done the job, then you let it pass through, and these would be typically microfiltration, ultrafiltration type of membranes, and then you can do a much more rapid separation of your sludge. This is becoming quite popular, and in fact, I've shown you this letter from Hubach, I think yesterday, and you can see that one of the things that they have also proposed is replacement of clarifier by membrane bioreactor. Obviously, must be that they also have this problem of rate limiting step of their clarification. What we have done up till now is that we have removed the organics. So let's assume that processes exist to take out the organics. But the problem is that there are many effluents where the problem is not necessarily organics. There could be inorganics. Of course, heavy metals, etc. We saw how you might be able to precipitate or maybe treat with an ion exchange resin. But when you've got loads of this salts, like saline effluent, like let's say you do an RO of very saline water, and then your reject stream will have very salty solution. Where will I discharge this? Those things are not going to come out with the kind of effluent treatment processes that we have discussed. One could be that if you use some method of precipitating those out. I remember there's a company and they had, I think it was sodium sulfate, and they were wondering what to do. And I looked at the phase diagram. It was very clear that if you lower the temperature, you can get the sodium sulfate to come out. So I asked them that instead of trying to strip off water, why don't you just chill it and take out? And so they could take out about 70-80% of the sodium sulfate. Obviously, the inorganic load came down. Of course, everywhere it may not be successful. Or if you have got this very saline stream, you could also consider doing things like bipolar electrodialysis that we talked about, and then see if you can regenerate acid and alkali. Because many times these salts are really the byproduct of a neutralization reaction. So there it would be good. Let me also show you another example. In fact, this is something for which ICT got a patent granted this year. This project has been set up in Latur in a small town called Ausa over there. And so there's an RO plant that has been set up under a project. People are getting the drinking water, but then the saline reject water, it wasn't very clear how exactly to solve that problem. And after looking at many options, including whether you can remove all impurities from that reject water and just be left with pure sodium chloride, and when maybe people can use it and use it for making lassi or cooking their food and things like that. I mean, if you can get rid of all the impurities, so that would be one way of solving it. But one was looking at alternative options, and so what has been done is that this is being put along with a concentrated fertilizer solution, something like muriate of potash, KCl, which is a good fertilizer. And now increasingly, all over the country, there's also a stress on doing not necessarily application of fertilizer and irrigation water separately, but you can actually mix the two together and do fertigation. That means fertilizer as well as irrigation are both being done together. So one made a very concentrated fertilizer solution and passed it through a what is known as a forward osmosis module, just to do standard osmosis. And from the other side, one passed this RO reject stream. Now the osmotic pressure of this concentrated fertilizer solution is so high that it effortlessly sucks out water from this RO reject, which is at a much lower osmotic pressure. And you can actually reduce the volume of this reject by what? I mean, about 70-75%. So first you recover maybe about 60-65% as drinking water from the feed water. then you're left with about 35% of reject water. And out of that 35%, maybe you can take off around another 70% by this spontaneous process of forward osmosis. And then what you do is that because the volume has got reduced, you may either, if you have got land, you may set up an evaporation bed, drying bed, and then try to remove all the water and convert it into a solid waste. But if you don't have that option, then you may have to do a forced evaporation. Now, naturally, forced evaporation costs money, requires a lot of power. So obviously, if you can reduce the volume of the RO reject to the maximum extent possible, then naturally, I'm reducing my evaporation load and I'm okay. So that's what it is. And then this fertilizer solution, which had picked up water, from the RO reject, so it's become dilute now. So the larger part of it, you can, let's say, put in the agricultural fields, okay, for fertigation, and a small amount, you can recycle back in your process after resaturating it with more fertilizer. So you again convert it into a concentrated fertilizer solution, and so you can keep operating your membrane process continuously by this technique. So what did you gain? One is that you reduce the amount of water for evaporation. Second is even for fertilizer, you require water, or you require irrigation water, and many times that is also in short supply, especially in a place like Latur, which can many times suffer from drought. So you can use a part of the RO reject water for giving water. And by the way, what permeates out is absolutely pure water. So none of the junk from the RO reject goes into the fertilizer. It's only pure water that permeates. And then you can recycle your whole process. And the third is, of course, where are you getting this water from? It's usually pumped from the groundwater. So naturally, you look at the pumping cost of pumping so much of groundwater, and then obviously you should try and maximize the amount of that water that you are utilizing. So through this kind of an integrated approach, you can actually do this. So that's the kind of concept, and believe me, it's a huge problem all over India. Why all over India? All over the world. That no satisfactory solution has been found to the problem of RO reject water disposal management, especially in inland areas. You can't, what will you do? Either you discharge it irresponsibly, which is what the majority of the people do, or if you are conscientious about it, then of course you need to find a cost-effective solution. And this is basically going towards that cost-effective solution. Any questions? Okay. Now, with that, we come to the end of water, and now I will start with fertilizers, and we will cover nitrogen, phosphorus, and potassium. Okay, so now we will come to the fertilizer which gave way to the greatest chemical process ever created, which is the fixation of atmospheric nitrogen. So how is atmospheric nitrogen fixed? What do you do? What's the process?
Haber's process.
Yeah. Why are you so hesitant to say it? Is there any other way that ammonia has been made, or you can make ammonia? Or is it only the Haber process? And believe me, there were other processes. In fact, there was a time when nobody gave a damn about the Haber process. That's the truth. We have, of course, learned that the first ammonia was obtained during the coking process of coal. It was found that there's a lot of ammonia in the volatiles. And that is what was used by Liebig to react with sulfuric acid and converted it into ammonium sulfate. And so ammonia really came as a byproduct of processing of coal. Things like liquefaction of coal, etc., was again very much talked about at one point, and it will be talked about again in the future. The second is that there were people who were quite ingenious, and so it's not as if Haber was the only one who was working on ammonia. So let me take you through a few of the processes, and believe me, I mean, if you read papers from 1906, I think they were very happy with the processes as those existed at the time. One of them was this beautiful process where they found that barium hydroxide could be heated with nitrogen and carbon, and it formed barium cyanide and carbon monoxide in water. It was a very high temperature reaction. But what they also found is that when they cooled it down and then contacted it with water again, the barium cyanide decomposed and it formed ammonia and regenerated barium hydroxide. So it was wonderful as an industrial process, that because I get back my barium hydroxide and I'm making ammonia. And this was not a bad process at all. Of course, it was very energy consuming because this particular reaction required high amounts of energy. But you can see that it is not as if nitrogen was only fixed by Haber. The other people had fixed it. Then around the turn of the 19th century, the electric arc furnace had been fabricated by Henry Moissan, one of the greatest scientists. And then he was doing this experiment, taking quicklime and heating it up with carbon, where I presume he probably thought that he will generate calcium metal and carbon monoxide, because otherwise there was no logic of doing this reaction. Why? Because so many metal oxides, you heat them with carbon and they'll get converted into carbon monoxide in the metal. That's a very standard process in metallurgy. So I presume, he might have thought that if he does it at a higher temperature that this reaction will happen, but that's not what happened. What happened was it ended up with calcium, forming calcium carbide. And we know what a revolution it was, because a lot of the synthetic organic chemistry really flourished after the birth of this process, because when you could convert calcium carbide into acetylene, not only for oxyacetylene flame, but acetylene as a very important chemical, which could then be converted into so many things. You reduce it, you get olefins, you can add things across the double bonds, and you can make a variety of compounds. And so there's no end to what you can make with acetylene. So it was a revolution. But what was remarkable was these people, Frank and Caro, they went in a different direction. And what they did was they basically tried to copy what these people had done earlier. Okay, and they cooked it up with nitrogen and heated it, obviously, and it got converted into what is known as calcium cyanamide. I've shown you the free form, which is cyanamide. And if you have calcium cyanamide, means these hydrogens will be deprotonated and there will be a calcium ion. So that's calcium cyanamide. And remarkably, calcium cyanamide, when it reacted with water, it formed ammonia and calcium carbonate. This gave birth to a very famous company called American Cyanamide. And many of these technologies I'm not even showing you, like cyanide synthesis, which then led to the recovery of gold. extraction of pure gold happened because of this sort of a process. I mean, the sky was the limit in what people could do after this had been developed. Now, this was a great improvement over this. The reason was that, you see, this I could only do in a factory. I cannot put this in the field, for example, simply because I can't waste my barium hydroxide, right? I have to recycle it. But that was not true about calcium carbonate, because people knew that it's a fairly cheap material, at least at that time. And so, what they said is, hey, why do I need to do all this in the factory? I'll just spread calcium cyanamide in the field, and gradually, it will decompose, it will form ammonia, it will get taken up by the plants, and calcium carbonate, if it forms, doesn't do any harm. There's so much of calcium carbonate in many of the soils. So it was a wonderful idea, and one of the most important nitrogenous fertilizers, cyanamide, calcium cyanamide. You're not seeing any Haber anywhere. Okay, and look, all examples of nitrogen fixation. But this is not what became famous. In fact, what became famous is what I'll show you next. In fact, in 1912, American scientists had set up a competition of the greatest technologies which were invented in the preceding 25 years or 20 years or something. And this competition was in 1912. And one of the prizes went to, there were two prizes. One of them went to the person who called the fixation of nitrogen as the greatest feat mankind has ever achieved. And this cuts across everything, because people realized that otherwise people will starve to death. Okay, but when I read it, what it said is that the electrical fixation of nitrogen, that is what was considered to be the greatest accomplishment. There was no mention of Haber in 1912. But before I come to that, this is again something that I want you to keep a note of, that you see, nobody today practices this, because everybody is doing it by the Haber process, the production of ammonia, and there's no question that it is a far superior process. But this did not die, this calcium cyanamide. And I'll show you, for example, a very, very important application. Like you can check with people who have diabetes. The biggest selling drug for diabetes is known as metformin, and that's got this structure, metformin. Okay, and guess what? Metformin is made actually from calcium cyanamide. So so you convert it into calcium cyanamide first, and under somewhat different conditions, when you pass carbon dioxide and water and raise the temperature, it actually becomes this. It then dimerizes this stuff into this compound, which is cyanoguanidine. This cyanoguanidine is then reacted with a dimethyl amine. You can work out the mode of attack and all that. I'm not going to go through it. It's quite simple, the mechanism. And it ends up forming this particular thing, and there is a positive charge, and that's why usually you'll get metformin hydrochloride or something. So that's what it is. It is a cationic drug, and this is the biggest drug in the area of diabetes. And when I asked a friend of mine in the US, where does all this calcium cyanamide come from, I realized that we don't manufacture it in India. I mean, only now I think there's one or two small guys manufacturing it, but all of it came from China and Mongolia. So, and look, I mean, this is been done around 1890. So so some of these golden things don't die. They find some other form, and not very different to nitrosyl sulfuric acid. which was the intermediate in the chamber process, and nobody uses it for the chamber process anymore. But nitrosyl sulfuric acid has not died. It is used to manufacture caprolactam. It gets quite interesting when you look at what all people have been able to accomplish. Okay, now let me tell you what became famous, and it owes it to initially Cavendish and Priestley. These were the two people, who had observed lightning. What they found is that lightning actually leads to the combination of nitrogen and oxygen, and it forms N oxides. And once I formed N oxide, converting it into nitric acid is simple. So they were not interested in making ammonia, and frankly, there's no need. I mean, I can even use nitrate as a fertilizer. So this was known and quite a very well-known thing. But Cavendish and Priestley could never make anything practical out of it. Then came, these people, first this pair of Bradley and Lovejoy, and subsequently these two gentlemen, Birkeland and Eyde. And so, these people, what they did was, they actually did, they simulated what Cavendish and Priestley had shown. They made an electric arc from these wires, and they passed a very high voltage so that it generated a spark, just like a lightning. And then, when they passed the air through it, they formed that, it's forming nitric acid. But it was a highly inefficient process. And what these two people did is that there was a person, a physicist, Julius Plucker, who had shown in 1860 that if this electric arc, which is formed, suppose they apply a magnetic field across this arc, amazingly, it spreads into a disk. It becomes a circular disk. You can imagine, if I've spread it out into a disk, obviously I've created a huge surface area for the reaction. So with that, they were able to make a practical process out of this thing. And I don't remember who among them, but I think one of them was Birkeland was a physicist and Eyde a civil engineer. And what were they doing? They were working on a chemical process. And that's the kind of thing that all of you need to think about. It's become very fashionable to talk about synergy and this, that. But these guys were doing synergy long, long ago. And look, physicist and civil engineer. There's no chemist over here who made nitric acid. So this became a very, very famous process. And mind you, for chemical engineers, another thing to note, by converting this arc into a disk, I'll send you this paper by Renouf, published in 1906, before the Haber process had been born, or around that time. And what it says is that the yield is about 100 grams of nitric acid per kilowatt hour, and advance on the 88 grams of the Bradley and Lovejoy process. So in terms of yield, Birkeland and Eyde did not achieve anything very spectacular. But then what he says is amazing. But this comparison in no sense represents the immense advantage of the Birkeland-Eyde process. The point is that with the electric disk, this disk, by applying a magnetic field, the inventors employ 500 kilowatts energy in one furnace, whereas by other processes, not more than 500 watts could be employed in one furnace. Now they could apply 500 kilowatts because it's stretched out over a large area. That energy is distributed. Whereas, if I'm only forming an arc, then the maximum I could apply was 500 watt. So we are talking about 1,000 times. a higher voltage. And thus Birkeland and Eyde can make 1,000 times as much acid in one furnace in a given time as any of their predecessors. We gloat over achieving an increase in the throughput by a factor of 5 or 10. 1,000? Unbelievable. Not surprisingly, it looks like those cement mixers, because Eyde was a civil engineer, so he probably thought of this design. And it's circular because this entire thing, that 2 meters, is you get a disc of that diameter, and air is being passed through, and there are many other complexities in this process. I'm not going into it. There are issues related to equilibrium, etc. Very interesting things. But I just wanted to tell you that enough was known about fixation of nitrogen. What I'll do is I'll just introduce you to the one more slide, and then we will stop. Now, nobody was interested in this reaction, which we now so famously call as the Haber process, and later on the Haber-Bosch process. And people didn't even know what is the thermodynamics of this process. And so the interest was really in making the nitrates from nitrogen, just like Birkeland and Eyde had done. But there's always someone who is thinking differently. And many times I find the Britishers, their ability to think in a very conceptual way is amazing. So what these people were doing was an interesting study. I'm sure what they probably wanted to do was to make some ammonia from nitrogen and hydrogen. And so these two people, Ramsay and Young, they took a iron catalyst, maybe because iron was available, so they thought they will use iron as a catalyst, and they heated it up, nitrogen and hydrogen, but they really could not find any ammonia. Now, after that, what they did was something very interesting. What happens if I take ammonia and heat it up? And obviously under anaerobic conditions, without any oxygen, because if you have got oxygen, then it will form water. So they completely excluded all oxygen, and they started heating up the ammonia. Again, must have been heated with a iron catalyst, some kind of a iron wire. And what was very interesting was that they found that the ammonia is decomposing to nitrogen and hydrogen. And then they said, yeah, that may be the reason why when we heated nitrogen and hydrogen, we could not get ammonia, because it's the reverse reaction which seems to be favored. But they also made a very interesting observation. What they said is that it doesn't matter for how long we heated, some residual smell of ammonia always remains. What does that tell you? If you get a residual smell of ammonia, what is it indicative of?
All the ammonia hasn't decomposed.
Right, but and therefore, if you express it in a with your knowledge of physical chemistry or chemical engineering, what will you say?
There may be an equilibrium, like
Brilliant.
ammonia.
Brilliant. That's all I wanted to know from you. I'm so happy. So the concept of an equilibrium in this reaction was born. And this is what Haber began to study. So on Friday, we will continue, and I will introduce you to the Haber process. The foundation is the work of Ramsay and Young. We will continue again on Friday, 1:30.
Thank you, sir.